So like I said, we're wrapping up Chapter 1 on properties of gases. And before we talked about what we called an equation of state. And if you describe these variables in the equation of state, you can describe, well, the state of the gas, its energy, and everything about it. We're going to introduce a couple of new equations of state today. And I've never really liked them because if you want to get the right answers for something, and then what you have to do is introduce little fudge factors. So, for example, if you want to predict what a human being's going to do, let's make that human being Eric. So you look up in a table and see all the little fudge factors that are specific to Eric and plug them in, and then you get all the right answers of how Eric's going to behave. Well, that's not a very good theory because it's cheating, right? Because you have this table that really has all the answers in it. So, but, that's what we're doing. And because real life scenarios, you want to be able to make much better predictions than what the ideal gas law gives us. So that's kind of where this is headed. But that's where we're at. So just talking about the ideal gas law, the ideal gas equation of state, and just how it's coming off and how good it is. Before we said what conditions the ideal gas law gives the best answers.
Really low molecular weight.
Like especially temperature and pressure. High temperature, low pressure, especially, right? Low molecular weight really helps too because things are smaller. But so instead of saying that, let's figure it out numerically. And that's what this compression factor, Z, and boil temperature are all about. So, however, in this compression, the reason why I say that is, doesn't that look like the ideal gas law? You've got a P and a V and an R and a T, except that, yeah, the N is missing. And you got this VM. What's that?
Molecular volume or something?
So what's missing? Before we had PV equals nRT, right? Now we just want PV over nRT equals 1. That is supposed to be the same as this. Instead of 1, they're just calling it Z, because it's 1 if everything works ideally, acting like an ideal gas. But what's the VM then? It must be what over what? Volume over volume per mole. V over N, right? The molar volume, right? That's what VM is. The molar volume, V over N. Okay. So if you get 1, the compression factor is 1, then it's acting ideally. Right? So if we take a look at this first plot, man, we do need a new lamp. Look, you can't even read these things. If I make it bigger, can you see it better? A little bit. Not really. Look, you still can't read it. Yeah, we better order a new lamp. Okay, so anyway, you can kind of see a little better. Where is this gas? So here we have a plot of potential energy versus separation. Separation between what, Shelby? What are they talking about? Separation between what? For this plot when they made it. Repulsion's dominant, attraction's dominant, contact. Yeah, when the two gas atoms are touching, that would be a collision, that would be contact, right? So just separation between the two molecules, the two gas molecules, right? Where on this plot would you say it's acting the most ideally, Jeff? What would you say? Where's this gas acting the most ideally? What part of this plot would you circle? Or would you circle the whole thing?
I'd say where the line, towards the word separation starts to.
Yeah. Why? He's right. Why? Why? In this area. Because if it's acting ideally, there can't be any what? Any attractions or repulsions? Because these are supposed to be what? If it's an ideal gas? Points. They can't attract or repel, right? So I guess you could say more ideal as you go that way. Like he's right. Okay. So if we take a look at this plot here, if I can blow it up. Whoa. Okay. This plot here, we can get rid of this one now. Move this stuff around. Okay. So we've got a plot of the compression factor Z versus pressure. And it's plotted for a bunch of different gases. Okay. And notice that Z equals what for all pressures if it's acting perfect? Z equals 1. And that's what we kind of sit over here, right? PV over nRT is 1 if it's acting ideally. Does hydrogen, this is hydrogen, right? You might be able to see it better on your printout there. It always exhibits what type of molecular interactions? Oh, yeah. Oh, we haven't really figured that out. Okay, let's go back a little bit. Here's our Z is always bigger or smaller than 1 this way. Z is always bigger than 1. Z here is always less than 1. Okay? So if Z is bigger than 1, what type of forces would that be? You only have 2 choices here. A hint might be over here. Well, there's attraction forces at an extreme, and there's repulsion forces at the other extreme. Those are your only 2 choices. Greater than 1 would be
Attraction, right? If there's a greater compression factor, is that like the amount they're attracting, or is it?
Well, to me, I look at the equation to help me out. I want this to be bigger than 1. I want this to be bigger than 1. So what type of forces can you correlate with P and V getting bigger?
High pressure, low temperature?
Yeah, what would cause higher pressure?
More molecules?
And again, now remember, we're trying to figure out attraction versus repulsion here.
Higher pressure would be repulsion, right?
Higher pressure would be repulsion. You can't, it's just a concept that you just kind of have to come to your own decision on, right? So if things are repelling, if that's the overall dominant force is repulsion, then yeah, they should exhibit higher pressures because they're repelling each other. Because these are real gases now, real interactions, and then they're all not going to have the same type of interaction. That's what this plot is saying. Look at hydrogen. Hydrogen never goes below Z equal 1. It's always bigger. So hydrogen always, at all pressures, always exhibits what type of molecular interaction? It always exhibits repulsion. Hydrogen always exhibits repulsion. It kind of makes sense because what's a hydrogen atom? Just a bare proton, right? So there's not much there to work with. So yeah, it's always going to be repulsion. Or dominant. Where's spelled dominant? Okay. So if Z is less than 1, you have what forces are dominant? Attractive forces. So what's being reduced probably? Yeah, that pressure. That's what I figured too. Right? Because the volume's a container. So you really don't mess with volume. So I'd say, yeah, attractive forces are really effectively reducing that pressure, making Z less than 1. Okay. The boil temperature is where the slope is supposed to be 0. You really got to zoom up on this thing. So that's what they did here. And they're trying to say, okay, what temperature can we use and get a flat line, right? So Z is 1, and things are going to be acting ideally. That's what they call the boil temperature.
NH is always less than 1.
Ammonia. Yeah, look at that. That's true. That's NH3. Didn't come out in your plot? Yeah, well, you might have to look at the book, too, because it's figure 1.22 in the book. So there's nothing really to memorize there. It's the concept, right? So if I gave you the plot and I gave you different gases, you'd have, oh, yeah, Z above bigger than 1 is repulsive forces that are down there. And if you really zoom up on this, where the pressures are extremely low, all right, you can get some flat line behavior. And where that it is flat, where the slope is 0, right? Wouldn't that be a slope equal to 0? Right? Change in y over change in x. Where that slope is 0 in that plot, they call that the boil temperature.
In that line.
Yeah, to get that, that's where the slope makes sense. You have to plot the compression factor versus the pressure. And where you get the slope to be 0, right?
So where Z equals 1.
That's where Z equals 1, yeah.
Is it going to be like exactly 1 or like roughly 1? You know what I mean?
Well, I think it's going to be Z is 1. Yeah, it has to be Z equals 1 because it's acting ideally. Because PVM over RT is going to be 1 then. Okay.
The slope, you said it was what over what?
Slope is just 0.
But the units on the...
It'd be the change in y or the change in x. So I guess it'd be the change in Z over the change in pressure. Change in the compression factor over the change in pressure. Okay. Variable equation of state. They call these expansions. And I don't know how much experience you've had with expansions, but if you get rid of these terms, just kind of block these out, you have the ideal gas law, right? So these B and C are our virial coefficients. Those are our fudge factors that I was talking about before. So you pick a gas, you have to look up different virial coefficients, and you'll get better answers than you would using the ideal gas law. Okay. And another thing with expansions is notice how they have plus dot, dot, dot. So that means there's a D over Vm cubed.
Does it follow a series or is it just random
And it keeps on going.
coefficients? Does it follow a series or is it just random coefficients? Like
No, they're going to give, like, let's say you're interested in hydrogen, methane. You pick the gas, you look up these terms, these virial coefficients, and then you plug them in, and you'll calculate the real life pressure. But you have to use the right fudge factors. And what I'm getting at is, another thing I'm trying to get at is these expansions, these terms become less and less important as you go along. So you're never going to see the D one because that D is so small. A lot of times you're not even going to see that one. You just look at the virial coefficient B for whatever the gas is, and they pretty much stop there. Okay. That's when this kind of stuff is important, right? B is actually going to be a significant number when Z is bigger than 1 and smaller than 1. But that B had better be what if you're at the boil temperature? What had that B better be? 0. That B had better be 0 because it's acting ideally. That's the only way to make it look like the ideal gas law. PV, so that RT times 1 plus 0, so yeah, you have the ideal gas law. So B would be 0 at the boil temp, but that's kind of the game they're playing there. And here's table 1.3, and they call it the second virial coefficient, V, right? Because, I guess you call that your first coefficient 1. So second coefficient is B. And they have it for different gases. And you have to look it up. And, if it's argon and you got 273, here's the number you use. And watch your units. Look at the funky units they give you. Okay. Let's take a look at this plot. What's an isotherm, Kelly? The reason why I ask this is, well, this plot. What's an isotherm? A plot where what doesn't change? Temperature. Temperature doesn't change. So what they did is they messed, right? They changed the pressure, monitored the volume, but they kept the temperature the same the whole time. Okay. So let's say we're at this 20 degrees Celsius isotherm, right? So we're keeping it exactly 20 degrees. We're at 20 degrees the whole time. And as you're decreasing the volume, the pressure is what? Going from A to B at 20 degrees. Pressure is increasing. That makes sense, right? You make the volume smaller, yeah, the pressure should go up. And you got to keep the temperature the same. So you're in some kind of bath that allows the heat to transfer through the boundaries. What do you call that kind of boundary? Diathermal, right? Okay, and then you get to C, right? The volume is getting smaller, right? The pressure's still going up. But when you get to C at this 20 degrees, all of a sudden you compress, pressure stays the same. Is that even possible? How could you compress a gas and not have any resistance, right? You keep compressing. Pressure stays the same the whole time. What has to be happening? No, the temperature has to stay the same because it's an isotherm. What's happening inside that container? What could happen to allow for those gas molecules to physically disappear? They turn into a liquid. What's the word? Starts with the C. Condensation. You condense, right? You condense. So at an isotherm, if you make the temperature of this room, right? Keep the temperature, get it in a container, and have a diathermal boundary so it stays at the temperature of this room and compress it. Sooner or later, it's going to turn into a liquid. It has to, right? So, and then once you get a liquid at E, it's all liquid. Look what happens to the pressure. Melissa, what is going on here? Look at that. Once it all turns into a liquid, the pressure just skyrockets. Why? You're trying to reduce that volume, but you can't. Pressure just skyrockets. What's so special about a liquid? They are the reason why hydraulics work. They are incompressible. Right? You can't compress a liquid like a solid, right? You can't compress it. So this pressure just skyrockets. You can't, yeah, I mean, it's minuscule. I mean, there's a slight change in volume there, but it's really nothing, right? Okay, so you keep playing this game. Let's make it a little bit hotter, right? And you keep playing this game, and everything, at some point, you reach a point where the pressure stays the same, it all turns into a liquid. Until you get to a point, in this case, 31.04 degrees Celsius, they have a little TC on it. And they say that, oh, we never hit the liquid stage. But you don't observe a liquid, but this pressure just skyrockets after a while. You have to reach a certain volume. That TC is the temperature, they call it every compound has its own TC. What's the TC stand for? Anybody? Critical temperature. Every compound has its own critical temperature. Above this critical temperature, you cannot tell the difference between a what and a what? A gas and a liquid. It's a whole new substance. They call it a, does anybody know this? Supercritical fluid. A supercritical fluid. You can't tell the difference between a liquid and a vapor. It's just, I don't know, it's too dense to be a gas, not dense enough to be a liquid. It's a very odd substance. You do this to CO2. Now I don't know how they figured this out, but whoever did is a billionaire if they patented this. How do you get caffeine out of coffee? Think about it. Caffeine is an organic compound, and coffee is something you do not mess with. You use some organic solvents to get the caffeine out, you're going to get other stuff out. You're going to have a hard time getting your organic solvent out. You're going to change the flavor. No. All you want to do is suck the caffeine out and leave the whole rest of the bean alone. For some reason, and I don't know why, supercritical fluid CO2 does the trick. And that's how you decaffeinate coffee. I don't know. How would they figure this stuff out? Right? So that's how they decaffeinate coffee anyway. So it's kind of neat. Anyway, that's what a critical temperature is. All substances have it. All substances have a TC. Like water has a density. Well, it's a property of water. Just like water has a critical temperature. Benzene has a critical temperature. All these substances have a critical temperature. Okay. So critical temperature, let's see. I think I have a video of this. I don't know if it's much of a video. Let's see. Heating above the critical temperature. I think it's it's benzene in there. So you can, you can't even see the liquid, can you? I can see it on my little plot. Oh yeah, you can kind of see it. Here's the gas and the liquid. Yeah, it's time to get a new lamp for this thing. And they're just heating it up. And at some point, at whatever, I'm not sure what the pressure is in there. See, the plot is, you can't see jack. You have to see it. Can you see it on here? Right? That's what you're supposed to look at. That's what you're supposed to see. See how before the boundary looked like, let me go back. I have to go further back. Okay, there's the boundary, like a typical boundary. It's already looking weird though, because where's the meniscus? Right? It did have a meniscus, but surface tension's already getting messed up. So they heat it up some more. See, now the boundary between the two is really starting to get foggy looking. Now all these little bubbles and stuff, that's, it's a condensation tube thing to keep everything the same temperature. You got this water bath thing going in there. And it's all made out of glass. So you're just losing the boundary between liquid and vapor. And now it's turned into a substance that's too dense to be a gas by our definition and not dense enough to be a liquid. Yeah, like a fog. Yeah. Except it's not condensed little droplets. Now, cooling below, let's see if this is any different. So here you're supposed to be starting with the supercritical fluid. Now you're just letting it cool. You just see the boundary forming. So all of a sudden you have a liquid. Okay. Let's see. So you can, now notice this critical temperature, you can measure it, right? What's big R again? Eric, what's big R?
Gas constant.
Ideal gas law constant. So you can, if you pick a gas, methane, benzene, whatever, critical temperature is measured. Gas constant we know. Some fudge factors. Look up a gas, plug in these fudge factors A and B for that gas, you'll get the critical temperature. So this is one way how they're, these constant, now these little A's and B's are not big B's and big C's. Here's virial coefficients. Here's the equation of state, virial equation of state. Now we're getting into a whole new equation of state with these fudge factors. You might have heard this one before, right? Van der Waals. So now we're talking about a whole new equation of state, van der Waals, okay? And again, you just look them up in the table to find out what they actually are. The A's and B's, yeah. Okay. We take a closer look at the van der Waals equation. There's some things that kind of make sense in it. Like, the volume is being decreased a little bit. And the concept behind that is that NB, your volume that you have is a little, I mean, it's so minuscule. But when you're talking about making predictions and getting the right answers, even the minuscule parts are what's important. The molecules themselves take up space. So the volume that's available technically to this gas is a little bit less because the molecules themselves take up space. So that's what NB is. The volume of the molecules themselves. So that's why the pressure is decreased a little bit. And then the pressure, notice how the pressure is this term minus this term. So the pressure is being reduced a little bit. So they're assuming what type of forces are dominant.
Compressive. The pressure's being reduced.
Well, you only have two choices for forces.
Oh, I mean, attraction.
Attractive. They're assuming that attractive forces are dominant, and it's decreasing your pressure a little bit. Let's see, I think there's only one last thing to talk about, and that's this principle of corresponding states. Oh, you don't have this. You don't have, oh, let me write, oh yeah, it is, it's there. Okay, what is this PR, TR, BR? They call them reduced variables. And what it is all you do is, if you want the reduced pressure, just take your pressure and divide it by the critical pressure, right? So in other words, that if we haven't talked about phase diagrams yet, but where does that, at what pressure does that critical temperature occur in its volume, right? So these are tabulated, all right? All the PC, you have TR, T over TC, for example. So these guys you find in tables, right? These critical temperatures and pressures and things. So for any gas, what you do is you just plug in the pressure that this gas is exhibiting, right? Divide it by a PC, look it up in a table, and you get the reduced pressure. It's just some variable, okay? Do the same with the temperature. What is the temperature of the gas? Divide that by its critical temperature, you get its reduced temperature. And what they're trying to say is, because what they're trying to do is clean things up. I don't know if they are or not. What they're trying to do is, it looks, and it's true, this equation is different for every gas. upside down A with a line is for every. Right? This is different for every single gas. Right? Because you plug in different A's and B's. But this is the same for every single gas. So that's the advantage of it. Why? Because of the principle of corresponding states. You get gases that have the same PR, VR, and TR. They're in the same state. And how do you calculate PR, VR, and TR? Well, here it is, right? Divide the pressure of that gas by its critical pressure and the reduced pressure. Okay, so van der Waals equation, different for every gas. Reduce variable expression, law of corresponding, principle of corresponding states, the same for every gas. Just realize you got to calculate that gas's PR, TR, and VR. Okay. And there's a homework question on that. You might want to do that one first, since that's kind of confusing. And I think that is, yeah, 29. I think we should do 29 first, because that's what we just talked about. And I think the rest of them are pretty straightforward, the rest of the homework questions. Kind of plug and chug type of questions. But 29 is not quite so much, I don't think. Suggest the pressure and temperature at which 1 mole of ammonia, do the same for xenon, same for helium, will be in states that correspond to 1 mole of hydrogen at 1 atmosphere and 25 degrees Celsius. So in other words, for part A, clean this up a little bit, right? You have ammonia. You want to know what the pressure will be and what the temperature will be. You've got xenon. You want to know what the pressure will be and what the temperature will be. And then you got helium. Right, for them to be in the same state. Now what the can you make the link that this is a law of corresponding states problem? Can you make that link? Right, that they're saying that you have these 3 gases, and they're going to have different pressures and temperatures to be in the same state as hydrogen at this particular pressure and temperature. That's a law of corresponding states. What they want you to do is they want you to use this what subscript am I talking about down here? They want you to find
Oh, that's not a circle. That's like a circle.
yeah, I'm trying to question mark.
C.
Oh. It's P9.
Because if they're in the same state, they have to be in the same P what and T what, the little subscripts. They have to be the same P, R, and TR that I'm driving at. Sorry. Right? You calculate this PR and TR. Because they said the same state as hydrogen. So you calculate what the reduced pressure is and the reduced temperature is for hydrogen. Calculate, and then if any gas, it doesn't matter what the gas is, you pick it, we can make it be in the same state. It just has to have the same PR and TR. Okay? So the first part, because remember, how do you calculate this stuff? PR is just P over PC. Okay? So if we know what PR is, we'll plug in for ammonia, for example. We'll look this up for ammonia. And here's our answer. right? This PR, where does that come from? That comes from the hydrogen data. Way over here. Does that make sense? So we got to calculate the PR and TR using the hydrogen stuff. And then to get all these other gases in the same state, just set their pressure over the critical pressure, or their temperature over the critical temperature, to be that reduced pressure or reduced temperature of hydrogens. All be in the same state.
So we do the same thing with TR, right? Like,
Yep.
That's what you're saying.
Yep. So let's go ahead and calculate this reduced pressure for hydrogen. Let's do this first. All right, it has to be P or PC. They said it's hydrogen's 1 atmosphere. Yeah, what's the critical pressure of hydrogen? Where do you find something like that? Google. Yeah, Google, exactly. It might be faster than, I don't know, maybe there's tables here. Very back of the chapter? Or the very back of the book, yeah. Usually there's this nice little table.
Is it that the PC equals A over 27?
There it is on page 33, but hydrogen's not in there. So you are going to have to go to the back. See, on page 33 is an example of this. They have PC and a VC, and they have them all. You even have the boil temperature, but hydrogen's not listed. So more values given in the data section. So we are going to have to flip all the way back there. Let's see if we can find it first here. I suppose it's going to be table 1 something, but on page 920. Page 920. There it is. Now it's helpful if you see it, because you want to get used to reading Atkins's tables, right? Gloria, what does it say for hydrogen? What is its critical pressure?
Oops.
Oh my goodness. Yeah, I suppose that's easier.
12.8.
What are the units, though?
Critical pressure over ATM.
Yes, what does that mean? What are the units? ATM. The units are ATM. So you said it was 12.8?
Yes.
ATM. Nice, because that's what they gave us. So divide 1 by 12.8, and you've got the reduced pressure. Since you tore out that page, let's calculate TR. TR is 25 degrees Celsius all over. Well, what's the TR?
For hydrogen?
For hydrogen.
33.23.
33. And what are the units?
Kelvin.
Kelvin. Good. Someone said that. So our Kelvin on top is going to be 298.
I wrote that down. And what's the critical temperature?
33.23.
33.23 Kelvin. So once you calculate those two, we can come over here. Oh, that's 1 over 12.8. 0.078. Oh, now we got to look up the critical pressure of ammonia for this first one, right? If you want to do this first part. What the heck? Gloriana, did you tear out that page too?
Yeah, it's right here.
What is it? The critical pressure of ammonia.
111.3.
111.3. And that's atmospheres, right?
Yes.
Okay. So 0.078 times 111.3, get about 8.69.
What's the critical for ammonia?
111.3 atmospheres. So for ammonia, here's half my answer. If you want ammonia to be in the same state as hydrogen at 25 degrees Celsius in 1 atmosphere, the pressure of ammonia has to be 8.69 atmospheres. Okay, now I'll go ahead and calculate what the temperatures are going to be. Does that make sense? If I lost you, just ask.
What would the critical temperature of ammonia?
405.5 Kelvin.
5.5.
Oh, so all these, anything with a C as a subscript, that's the critical.
Oh, that's.
So that means you have to get them in tables and look them up for that gas. So that's the critical pressure. That's the PC. So in the only place is the back of the book, and you find, since she tore it out.
No, it's 405.5.
All right. So you need to find, we're talking about which gas? Ammonia. So where's, here's ammonia, and there's its PC, 111.3. So all these critical pressure, critical volume, critical temperatures for all these gases, you don't memorize them, you look them up.
That's the face I made when she said that when I started to laugh.
I can't believe you
Sorry.
modified my book.
She like whispers these jokes to me so nobody hears her.
Take that back and place. Okay. So who's all going? I can shut this off. Who's all doing the pizza thing?